Today we're going to talk about classification under misspecification, aka learning half-spaces under Massart noise. So what is half-space? It is a linear separator and it categorizes data based on the threshold. So if the data is above the threshold, label 1 is assigned. Otherwise, label -1 is assigned. Now let's look at 3 different noise models. Massart noise model is in between random classification noise and agnostic noise. RCN noise model is a noise model with fixed noise rate that is under 0.5, and agnostic noise model is basically just random noise. So Massart noise is a combination of random noise and with noise rate under 0.5. The reason that the noise rate cannot reach 0.5 is because it's not packed learnable when noise rate is 0.5, since every label seen by the algorithm is the outcome of an unbiased coin flip and gives no information about the target concept. That is, when the noise rate is 0.5, 1 minus the noise rate is also 0.5. You can figure out which one is which. So for the prior work, we can see that the scientists discovered improper learner and proper learner of half-spaces under optimal error. In this presentation, I'll introduce proper learner algorithm, and their idea is to use min player to find out the hypothesis W and use max player to find out the region where min player is doing poorly. The max player will reweight the poorly performed region. Therefore, they can find the optimal hypothesis. So for the algorithm, they first initialize a random W to a vector in the unit ball. Then the max player is going to find the slab that maximizes the leaky value loss in that slab. So if the best slab in the max player he found can produce a loss that is smaller or equal to epsilon, then the hypothesis will be returned because the noise rate is low, it doesn't affect it that much, and the hypothesis is accurate. So if the max player finds the slab where loss is really large, they're going to exploit the convexity of the loss function and they'll get the opposite gradient and project back to the unit ball. So now let's look at the results. As we can see that the first column is applying 4 different algorithms under RCN noise model, and it seems that all of them performed really well. But on a Massart noise model, as we can see that as noise rate get larger, there's a really big drop of accuracy and for different demographic groups. So basically, the proposed algorithm is the best solution to learn half spaces under Massart noise. And we also can see that the random forest also performed really well, but it does not return a half space. So we will discuss it here. But it's also remain an open question in the original paper that they don't know the reason why random forests can perform this well. So now let's talk about my implementation. I utilize KN to learn half spaces on the Massart noise. I first initialize size of neighborhood K and number of samples n, and I draw in samples from the cropped distribution, and then I use following classification rule to categorize the point. I determine the set of labels in the neighborhood, and then I get the average label in the neighborhood. If it is larger than 0, I will return 1 as the label of the entire neighborhood. Otherwise, I'll return -1. Now let's see the input I created. I used to Gaussian distribution and cropped it with the Massart noise. As noise rate get larger, we can see that it is more cropped. Now let's look at the results that when noise rate get larger, we can see that more K values is required in the neighborhood, which is normal. And the overall performance is really good. And we can see that no matter what noise rate it is, it can get a accurate separator.